Hello and welcome to my talk about open telemetry and distributed tracing with a subtitle of what's actually my distributed AI system actually doing. So what's my distributed AI system actually doing? I was talking about that at recent CLC conference in Mannheim and also gave a similar talk before. So welcome to the new spaceship observability, the next generation. And the Starfleet has decided that they also need AI these days. I mean, the Romulans have AI, so they also need that. And everyone knows it. There is this guy here, the captain, and he likes tea, Jean-Luc Picard. And then the famous quote is tea, Earl Grey, hot. And he goes to the replicator, puts a mug under it, and you probably know it as the coffee machine. And it's taking time, and then finally a drip of tea is coming out, or of his Earl Grey, and this is not satisfactory for the captain. So he's calling his first engineer, Geordie, why is the replicator so slow? And Geordie is coming, saying, let's see, on screen. And they have this big, huge screen, and they look at the diagram, and the captain is not happy. That looks complicated. Is there no way of getting that in a better way? And yes, there is with open telemetry, especially the tracing part. So I'm Heiko. I work for Red Hat. Um, yeah, and what I'm going to show in a demo in a few minutes is something that looks a little bit like this architecture. So a request comes in, that's the black arrow, goes to a Quarkus app, that's the blue box, which then talks to a database to figure out which keys are available, talks to a Python service, that's a payment gateway, so you probably know that from the enterprise. You don't get a free coffee, you have to pay 30 cents or something. And this Python code also looks up the price of the tea in the database, and then also contacts another service, a third party, perhaps something like an external payment provider or such. And that's an architecture that probably every one of you knows. And to get that prepared for tracing, we have these purple boxes. That's the instrumentation. That's basically where signals are detected, collected, and then later sent off to our tracing system. You see we have that in many places, so we need that for incoming requests to know when this starts and when it ends, but also need to talk to the Python server so that we know when we start talking to it and when it replies and if how much time that took. And there are these smallish green, light green boxes. These are trace exporters. So this is basically a subsystem within the server process that sends the traces off to a central collector, which is the brown box on the bottom left. And this then forwards that into a trace metric database and a UI to watch at that. And sometimes, like in our example, the brown box and the black box are collapsed into one with this Jaeger all-in-one image that I'm going to use. But we also have other situations like in Kubernetes where you have one of these collectors as a node agent on each node and then a central database and UI for it. And now a little bit of theory. What is a trace? What is a span? Basically, we want to trace calls, incoming calls. So when there's this request coming on the left side into the blue box, it's forwarded partially into the database, but also partially into the Python service, which then also calls the database and the other service. And on the right, you see that there is this outer blue line, which is basically the start and end of the request that's coming into the blue Quarkus app. And within that, you see we have this greenish block, which is basically the time to call into the Python service, which itself is calling to the database, the red one, and the other service, the orange one. And then afterwards, or before, we'll see that in the reality. The blue app, the Python app, the Quarkus app is also talking to the database. And all these little blocks are called a span, including the blue one. But as the blue one is the outermost, it's also called the trace. And for, let's say, the red span, the blue one is the parent span. So there is a parent-child relation in here. One parent can have many children, and children can have siblings, as you see with the red and yellow one within the green span. And so we can create a hierarchy or a graph that we can later look at and inspect. Before we come to the demo, let me quickly um, give you a little bit of a why we want to do that, why we want to do the tracing, the instrumentation. On one side, we do have the logs, we do have the metrics already, so why do we need that? Um, Usually it's the metrics give you something like the CPU usage, but it's not tailored to one single request. So if the CPU is at 20%, but your user calls in and says, hey, tea brewing is slow, the CPU usage doesn't help you at all. Likewise with the logs, if it's on one system only, they are kind of easy to parse. But here we see that it's a Quarkus, it's a Python, there may be some Golang and some other systems. And they will all have a different log format, and then matching them together, so bringing that all in one format, putting it in one place and making sense out of it is also pretty hard, because we don't start with a structured way of exporting logs in the first place. And then it's kind of shoehorning the structure later. We could do a better job, and actually within OpenTelemetry there is also a way of sending logs together with the traces or in a different channel. So this could improve the situation, especially if we have the trace ID in a log, so that we can see in the log if something is fishy, then we can go over to the tracing, or the other way around. If we see a trace that has an error and I show that, then we can go to the logs if we see something with the same trace ID that gives us additional hints. The other reason why we want to do tracing and the instrumentation is especially in the light of Kubernetes clusters or OpenShift, where Kubernetes can kill your pod at any time, and it's getting even worse with serverless, where serverless gets a request in, does something, and then terminates. There is the classical way of Prometheus calling in every 20 seconds, may or may not miss that process, or may not miss the latest metric. The other effect that I've seen often in production is developers and even the admins do not have the possibility to open a shell on a pod and do a PS or attach a debugger to or profiler to see what's going on. And worse, if they attach a debugger, the debugger may stop the process. Kubernetes health check will fail and they just kill the process where we attached the pod, where we attached the debugger to. So that is not a way. So it's really important that we export the signals from our workloads into a place where we can then analyze them. And it's probably a good idea to always have at least a 3-day of backlog of trace data or observability data at all, so that the crew can investigate potential issues on Monday and don't have to come in Sunday just because the time buffer is too short. Okay, let's go to the demo. Going over here, so I have this replicator. Let me start that. So what T do you want? And in the old one, we had we were just Captain Picard had to type in the T that he wants, but this was not good. This is also why the Starfleet invested in AI. And you see it's taking a bit of time, and let's see what happens. Okay, so apparently that T is not on the menu. What I can also do is I use the speech recognition of my Mac here. I want some Earl Grey, please. So and now we again call into the service. And you see this is something which would be pretty, this is something where parsing the human language and different languages is probably a tedious thing. So there is a LLM that's basically parsing the text and extracting the T's. And apparently this was kind of successful, but there is not enough dilithium available. It's possible that we are in a war situation and the dilithium is needed for the weapons, or we are flying at warp 9, and so that has more priority than some T. So let's try some other one. Ich möchte bitte einen Sencha. Funnily, that is not Sencha, so the speech recognition did from the laptop did say it's a sender, which makes no sense. So let's see what's happening. Okay, apparently it wasn't able to detect what it is. So let me manually switch. So probably a better LLM than my little Quen 3. 4B would do a better job here. And here you see now it has correctly passed the sentence. And now when we go into our tracing system in Jaeger, we can go to the Jaeger UI. I have a look back of last hour. This is why there is already stuff populated. Actually, it's because of the calls that we just did in the last few minutes. And this is the first one, I guess, with yeah, so basically what we see here is the full trace. This one had 17 spans in total. It took 7.5 seconds, and here we see the timing diagram in an abbreviation. And down here we see the details of it. So first, the incoming request from the UI called the getT method, and we can open it here. And the tags says, okay, the client is also on localhost. We were calling the class T resource and the make T method of it. The detected T was Sencha. I'll show you how we get this. Was a HTTP GET. We had a 200 response because it was good. The internal span format is OTLP. Server port 8080. This was the query URL, the query path, and the user agent. And this one then did do a post for tparse, and this took 6.3 seconds. And we can see that this now is a different process. The T agent, you see here, before it was the replicator. Now we have the T agent process. So this one is the server side, basically the HTTP receiver. And here we see this is the class tparser web resource and the method parse tpost. This was a post request. We got a 200 response. So that looks pretty familiar, I guess, with what we saw before. Where it gets interesting is that the next call, this one is then going into agent AI service.parseT, and this agent service is calling the completion of Quen 3.4b. So this is now a call into our LLM. Here you see the GenIA request model is Quen, temperature 02, finish reason stop, so probably because it found the T. And then we already finished in here. I'll show you something different later, I guess, I hope, because there should be a tool call which hasn't happened, which we can see because it's only this completion but not the subsequent tool call. The next step was then that we get a data source, a database connection, and we fired a select against the database to basically see if that T that we just detected via the LLM exists. And if we open it, we see here in the tags again, there is a connection string to the database, so it's a Postgres on localhost with the name of replicator. That was a select operation, and here we see in the DB statement, this is the prepared statement that was fired off, which is then something that we could, if that would have been slow, that we could go to our DBA with, and they could help us debug it, and perhaps sometimes we figure out we just did a linear scan through a million rows, and because we forgot to set an index. There are some database drivers, and I heard that Oracle is one of them, that can even set the execution plan here to basically help even more with debugging. So you don't see the parameters, but at least the execution plan. And then when this was done, we do a client a get request, HTTP method get. Here it's a client span, so we are calling this external service, which is our payment gateway, and we saw that it was returning a 200. And again, as this is instrumented, we see here a new process, this payment process. It has an HTTP handler, does a GET request and then a select, and I show you the select here. The DB statement format is different because this is now in Python, and the Python instrumentation just records that differently than what the Java instrumentation is doing. What's probably also very different in the Java world, it was a prepared statement or a statement with parameters that's fired, and here it's more literally the one that I've basically typed in my code. And then finally, now that we know that the payment has happened, so collapse that. There is a topic publish on a Kafka topic, and then another job, a Kafka relay, that's basically has received the message, is doing some work on it and sending it off, and the replicator is receiving it. What's interesting here is first, we don't see how the T is created. The T is brewed. It's just happening here. So we only see the whole trace is over here, but actually sometime over here the real job, so the answer would already have been returned. We can see that here from the greenish lines at the top. So let me go back. This is the 6.9, 6.7 seconds for the get T, but overall it's 7.5. So there is kind of this part is still missing in here. So let me go over into my IDE, and then into the code, which is the T resource. Here you see it's a Java method annotated with @get. So here we will listen on localhost 8080T. We first check for the if there is an input or not, and here we see already an annotation span attribute requested T input for this input parameter, which we can then later see in Jaeger. Actually, we should just go in here and the tags, where here it's called detected T, but it's basically the same. Here T request input. Then here we go into the T extraction service, which is my LLM parser, LLM AI agent basically for the T extraction. And then we set here the detected T. That's the one that I was just showing you. And then we are going to the database, find by name, then go to the to the payment gateway, and then we are going to the brewery and brew tea, but this was not visible, and this could be slow. I mean, could take. I mean, we have seen this replicator was pretty slow in creating our tea. So let's go over there into the brewery service, and here in the brewery, I guess I have to start my application. The default is when you do Java method calling that spans are not recorded for methods, but if I annotate with add with span, then a new embedded span, a new internal span was created for this method call. And again, I can here set a span attribute that will then be recorded as well. So let me restart the service and let's retry again. Okay, here we got a payment exception. That's bad. So let's try the Sencha. And while this is running, I head over to Jaeger, into the Jaeger ID. Then I head over into the Jaeger UI, click on Find Traces, and we had the, well, this may be probably the latest, as it says a few seconds ago. What I actually was expecting or wanted to show you here is this one is marked as error, and then the replicator process has shown an error. So let's have a look at that. We see the top level, this was reporting an error, and here we also see very nicely how the LLM was first doing the completion, and then the response told us that to call the get brewing instructions tool. So this tool was called by the agent process, and then with the information of the brewing instructions, the LLM was called again to get the final answer, which was then replied to us. And somewhere down here, we saw here in brewery brew tea, this is marked in red, we have an error. So we can open that again. And if I go in, it's calling brewery brew tea, and it says no dilithium available. So we have seen that before. So it can't brew the tea because there is no energy. And then the error flag of open tracing is set. This was an Earl Grey requested. And with this error flag, this is then bubbling up, and then the entire trace can be marked as a faulty one. As a bonus, we also have for this exception, because it's a non-called exception, we get the exception message and then also the stack trace, so we can directly see this is coming from brewery.java at line 40. And if we go to brewery.java line 40, we see indeed there is this exception. And then we are also setting the attribute of the span with no dilithium. And you have seen here the span attribute of kind of tea, which is then the tag over here. Where do I have that? Here, kind of tea Earl Grey. Okay, so with this information, we have the we do have a lot of information recorded here, and one could, for example, be the tags. So we could see kind of tea equals Sencha. Okay, now we have a kind of tea, and we only get traces where the kind of tea is set to Sencha in one of the span attributes. So here you see 2 days ago at 12 p.m. there were 3 requests, and then this is from today, so I can go back to last hour, I guess. So, and then we can also say, because normally it's probably relatively non-interesting to us to see all these successful traces. What you really want to see is the ones that are outliers. So we can also say error equals true. And then we see only the red dots one. So the one that we just had over here. So you can find the outliers or the traces that have a problem. Likewise, we can ignore that. We can say we have a baseline, and normally brewing a tea takes whatever 1 second. So if it's taking more than 2 seconds, there is probably a problem. So let me try if 4 seconds is a good cutoff. So we have 2, 3, 4. This was even 15 seconds. This was, I don't know, 10 seconds. Was quicker. So let's do a cutoff of 10 seconds, and then at least this one should go away. Right, you see, now we only have filtered those that are 10 seconds or more. It's also possible to say it the other way around. Everything that has a max duration of something, like for example 1 second, because if we know that brewing a tea always takes 10 seconds plus, getting a tea being brewed, getting a tea being brewed is only 1 second is a clear indication of an error, because then the brew process could not have happened. Okay, this is not what I'm expecting. Oh, okay, down here it looks odd, but it's a max duration of 1, so they all should not, well, almost all should not show. Perhaps it's a combination, I'm not sure. Anyway, so that's that. One interesting thing is now, and let me go back to my slides. The instrumentation, how do we do it? And within Quarkus, it's pretty easy. A lot of that can be done pretty automatically just by including these two dependencies. The first one for general open telemetry and distributed tracing, and the second one for the database tracing, the JDBC tracing basically. And then you can also do some by hand. We have seen that, like with the add with span, where we say, okay, we want to measure this Java method, which is just called from somewhere else, because this is business critical. We do complicated computations, or we render an SVG down to a PNG because some strange browser is not able to render an SVG or whatever. So we want to especially measure that one. The interesting question is now, how does that Python service, and we haven't seen that yet, how does that Python service know what the parent is? And what we do is, there is a way of propagating the context. Let me fire Wireshark, not only for the slide, but let's do it in real. So we do a port 8787 or port 80,000, and then we do a filter of HTTP traffic only. Go to the replicator, another sensor, and if we go back to Wireshark, this is now taking a moment, because you've seen with the LLM parsing. We got now this request on the payment service. If we go down here, it's IP, it's Internet Protocol, source IP, then it's TCP with a certain destination port, and then we have the HTTP part, and these are the HTTP headers. And here we have get payment, accept header, and then the trace parent header. And this is standardized, that it's always trace parent, and then there is the version number, there is the out or span ID, so the trace ID with EA something something, and then here the E4, E8 one. That's the actual parent ID, and then we do have some flags, this 0, 1. So we can have a flag and say, okay, do not record this trace. For example, we have instrumented all incoming HTTP requests, but Kubernetes is doing these health checks every now and then, and we do not want to record the health check. So we can basically, the gateway can set a flag that if this is for the health request, and the health request may even call into a different service, that we just don't want to know about this trace at all. And then we see here the outgoing one. This should still be EA5A. Let's check that. EA5A, so it's still the same parent, but obviously the same trace, but obviously the parent ID has changed. So now the instrumentation in Python. So here, this is my Python code. Don't be alarmed by all the wiggles. That doesn't really matter. Let's start at the bottom. This is here, if name is main, then we start doing stuff, passing a few arguments and so on. And then we are doing two things. First, for the requests library for outgoing HTTP requests, we add auto instrumentation, meaning we don't have to do anything anymore about that. And the same for the database connection, so that we get the SQL statements traced. And then we start with setting up the exporter. We give this a service name so that within the trace view it shows up as a trace, a payment service. We set up the trace provider with this name, tell it that it's sitting on the endpoint of localhost 4317. We create this span processor trace provider. You can have many exporters, so you can have an exporter that's talking to the hotel collector, but also to console. And then finally we are setting up the tracer, getting a database connection, and then starting the real serving of the server. And then within the my request handler, what we do is a do get request, and for each incoming trace we look at the header trace parent, and if this trace parent is not none, we all print it on console and then extract the trace header data. That's basically a bunch of regular expressions to get out the parent ID and the trace ID. And then we set the current span in the context of the parent and the trace. And then we say with tracer start as current span with the name of do get handler, do the following block. So in Python, stuff is indented, a block is indented. If the span context is not none, we are getting this context just for the logging. And then we do some stuff. We do this outgoing request with the requests library. We do simulate a bit of slowness just for the showing. And here you see for span we say set attribute request line. So basically we are just getting the request line and then setting that, and if there is a question mark missing, we do that, and then set a 400 response, basically saying this is an invalid request. Otherwise we send a 200 response, set the span attribute of t kind, do the get payment method, and response, reply back with the response, and here in get payment. Basically, we talk to the database. Here you see this select statement. Sometimes it's taking longer because there is an artificial sleep, and then we would see that in our trace. So this is in Python on one side kind of auto instrumented for the requests library, but also kind of manually done over here with setting the span attributes. Setting the span attributes is something that you um, there is even more auto instrumentation by a library that's loadable, and this also exists for Java. But in reality, you very often want to record some business attributes, like what browser are people are coming in? Is there a slowness when they come with a certain kind of browser? Or is a VIP flag set? Is this a VIP customer um, or not? And then later you can search for, is this a VIP customer or not? Here we see it again, the trace parent HTTP header. First is the version part, the trace ID, the span ID, and the flags. And we have seen the trace view in Jaeger already. And this is another one a bit more complicated. And then here what we have seen is when we have the AI agent, we can see actually what is doing inside the agent, so that it's calling the completion method, so doing the post and talking to the LLM, and then doing the tool calls, and then getting the tool result back into the LLM for further processing. So this is pretty interesting. This is a bit of an older trace view you see from July 25 of Llama Stack, where I was doing some Python code talking to Llama Stack, and the model what is itself was running on an Ollama server. And you see a lot of stuff that's going in here, like register MCP server, calling the tools, and whatnot. At that time, there was no context propagation from Llama Stack to the external tool provider. So the traces are not really complete or end to end, but you can already see a lot what's going on within Ollama here. And the TLDR is our captain has some tea. He says that's delicious and hot, and Jordi is also happy because it's fully observable. And there are some links. So we do have the repository with the example code, OpenTelemetry.io, and that's it for the moment.